Okay, please, let's take our seats because we are not, we have the time. Okay. So I think we start the last session of this Jornadas CPAN. And we start now with Irene Valenzuela from IFT, UAM, but also from CERN. And she's going to talk about exotic landscape, the swampland program.
Okay, thank you very much. Can you hear me well? Good. So first of all, of course, thank you very much for the invitation and the opportunity to talk about this topic, which I find very exciting. So I'm very happy to share with the Spanish community an overview about the swampland program. So I will tell you what is the state of the art, and I will give you just a few examples so that hopefully they are useful to convey why this is interesting or why we are excited about it. So let me start with the following question, which is, does quantum gravity matter at low energies? Okay. Now, the answer that probably is coming to your mind is that no, probably not. Not as far as we know, maybe. But why not? Okay, what is the intuition that makes us think that it's difficult to get implications from quantum gravity in experiments that can be accessible today? Okay, so why not? Well, modern physics is based, as you all know, in a Wilsonian effective field theory approach. We love to construct effective field theories that can describe the physics to some energy scale, some cutoff energy, so that we can describe what we observe without worrying too much about the UV, about what happens at higher energies. So this Wilsonian approach is not necessary, but comes together with some expectation of separation of scales, in which you expect that you can describe the physics without knowledge of this UV completion, so that the IR physics should not be very sensitive to the microscopic description. And this, this is not just a desire, that so far it's an expectation that so far has worked super nice. Okay? It has been super useful, and we have progressed a lot in high energy physics this way. Now, since quantum gravitational effects are typically expected to become important at very high energies, in very small distances, this is what makes you think that the answer to this question is no, because this is, today we cannot access these high energies, so the effects will become irrelevant if I'm just interested in what happens at low energy scales for particle physics or even for cosmology that is below M Planck. Okay, so the message of this talk is that I want to convey the message that this is not necessarily, this is wrong. This is not necessarily true. The story can be more interesting, okay? And the reason is that gravity is different than the other interactions, okay? So the point is that quantum gravity breaks this notion of separation of scales, and therefore have the potential that we need to explore of providing non-trivial constraints at low energies. So why is that? Why we think that gravity is breaking this separation of scales? Why is mixing this UV and IR? Well, we have evidence from string theory. In string theory, there are many examples in which you see that there is a correlation between IR, like long distance, short distances, and so on. But even beyond getting into all the details of string theory, already thinking about black holes can give you at least a qualitative intuition to understand why there is this UV IR mixing, okay? This mixing between high and low energies. So just to give an intuition, we are used to collide particles, right? So we want to explore the physics at smaller and smaller distances, so we collide particles at higher and higher energies. But if we continue doing this, at some point, what we are going to create is some black hole. And if we continue adding energy to the system, instead of probing smaller and smaller distances, the black holes are getting larger and larger, so we start probing larger and larger distances. Okay, so this already manifests some correlation between long and short distance. Now, the fact that there is some correlation, and that in particular string theory can impose some UV-IR mixing, I think it's clear if you think about it from string theory. The difficult part is to make this precise, okay? Like to understand how strong is this UV-IR mixing and whether we can make something useful with it, okay? This is the hard part. Now, if there is some UV-IR mixing, the first thing that is important to notice is that then not every effective field theory is compatible with quantum gravity. And it's not only about the tower of non-renormalizable operators, it's not only about the corrections that become irrelevant, but the EFT, like the renormalizable part, can receive an impact. And therefore, you have to be very careful when you just work from bottom up, because your favorite model maybe is not consistent, it's not compatible with a quantum gravity completion. Okay, so this is the message that if you imagine the space of possible effective field theories, not all of them are necessarily consistent with a quantum gravity description at higher energies. So not every effective field theory can arise as the low energy limit of a consistent theory of quantum gravity. And those that are not consistent is what we call that they belong to the swampland, okay? In opposition to the landscape, which is the traditional word that is used for those theories that can arise as low energy limits of quantum gravity. Okay, so the swampland are those apparently consistent, like for instance, anomaly-free, quantum effective field theories that cannot be UV completed in quantum gravity. And the goal of the swampland program is to determine what distinguishes the landscape from the swampland. So try to make this precise and understand what are the constraints that an effective field theory must satisfy to be consistent with quantum gravity. What do I need to require? I need to require this anomaly-free. What else? Do I need to require some specific bounds on the higher derivative terms? Also on the value of the couplings, the masses? What's important? No? What are the rules of the game? Okay. Now, of course, this is a very ambitious question, right? Because understanding quantum gravity, it's a big challenge. We don't have a full framework that for sure includes any possible quantum gravity description. But it's very exciting and very important because even if partially we aim to understand this UV imprint at quantum gravity at low energies, this can have interesting implications for phenomenology, okay? Because sometimes what we realize by studying these possible constraints is that the results are surprising in the sense that they break some of the EFT expectations that you could have. So it's kind of a golden opportunity to try to say something new. Try to say, okay, maybe this is the expectation you had from bottom up, but from a quantum gravity perspective, the rules are different. So why there is so much activity? Well, like in the past few years, there has been a lot of activity regarding the swampland program because it started as a new approach to try to connect string theory to the real world. And since we are in this conference, and yesterday we were also discussing a lot the role of the Spanish community in the different areas, I just want to mention that, there's this mini revolution that is happening in string phenomenology that started in 2015. And it was led mainly by Spanish physicists, okay, among a few others, so it's something nice to know. Okay, so as I said, the interest, the long-term dream is that we can say something new, something useful, no, for particle physics and cosmology. So the goal is trying to make this UV-IR mixing precise so we can give potential phenomenological implications and use these new constraints as guiding principles to construct beyond standard model physics and so on. And also my dream actually is to see if we can use them also to provide new insights to solve the naturalness issues that we observe in our universe. Because the whole point is that not the entire space of parameters is allowed, so all the notion of fine-tuning and so on have to be revisited, and what is natural or unnatural might change if you take into account what is already possible or not possible. Okay? Okay, so what are these constraints? Okay, so here I have like some map of some of these most important swampland conjectures. Let me use this to tell you a bit just about the history of what's going on with the field. So 7 years ago is when there was this revival of the swampland program. So these were some constraints that were actually formulated like 15 years ago and so on, but there was no much activity around them. And it was only 7 years ago when we started to think about this more detail, because we realized that they can have implications for the world, and then there was excitement about it. No? Okay, maybe we can say something new. So this was the status 7 years ago. After that, there was a lot of activity, so then there were more conjectures appearing, more constraints, and so on. And after that, in the past few years, what is happening is that we realize that all these statements are actually connected to each other. So the focus now is on the relations, okay? To try to reduce all these constraints to the minimum set of statements that could reproduce everything, because these relations hint that they might be just different phases of the same quantum gravity principles that we are starting to discover. And in the past, I would say this year and last year, like the past 2 years, I think we are entering some, I like to call it like some era of precision, because instead of just studying qualitatively these features, we already are gathering enough data, like enough information from string theory, holography, black hole physics, to address also all the subtleties and test the conjectures at a quantitative level. Okay, so once I've said this, of course, in this talk, well, maybe let me come back. I cannot just describe everything. There's no time. So let me just focus on these two that I put on purple. Okay? I'm just going to review what these constraints are, because these two are at the core of the swampland program. And I will give you just 2 examples of a possible implication coming from these 2 conjectures. Okay, so let's start with the first one, which is the absence of global symmetries. Okay, so the statement is that, indeed, there are no global symmetries in quantum gravity. They must be broken or gauged. Now, if this is the first time you hear about this, you should be surprised. Like, what do you mean there are no global symmetries? Like, symmetries are super useful in physics, right? We love symmetries. It simplifies our life. And we have, I mean, they have been super useful to improve our knowledge of the universe. So I don't mean that there are no symmetries. What I mean is that if there is any symmetry which is exact, it must be associated to some interaction in some gauge field or gravity itself. Okay, so global symmetries that are, like, for instance, this rotational symmetry that is not associated to any interaction cannot be exact. They must be broken at some energy scale. They are just approximate. Okay, so it's very important to understand this difference between global versus gauged. Okay, so let me explain it a bit more. Let me also remark that here I'm talking about symmetry, so I'm not talking about local transformation, redundancies, or anything like that. It's really conserved charges that have an impact on the physical states. Okay, it's just that you can have global symmetries or gauge symmetries like the electric charge. Okay, so the intuition, I mean, of course, there is a proper way to define the difference between the two using the formalism of topological operators and so on. But just for today, let me just give you some physics intuition of what is the difference between the two. Okay? Because this will also be useful to tell you later why the global ones are problematic in quantum gravity. Okay, so the intuition is, if you're interested in understanding the difference, you must ask yourself the question whether you can measure this conserved charge associated to the symmetry from far away. Okay? Whether you can carry information somehow away from the experiment. And the point is that gauged charges, so symmetries that are gauged, you can do it, while global symmetries, you cannot. Okay? So let me give you one example, which I hope is familiar to all of you. You can consider the standard model of particle physics. You can consider this decay. And here there are two conserved charges. One is B minus L, baryon minus lepton number. And the other one is the electric charge. Okay? Both are conserved in the standard model. But the first one is global, while the second one is gauged. And it's clear because also if you are very far away, because you have the electric field, you have a Gauss law, you can measure what is the charge that is inside of the box, even if you don't open the box. But to know what is B minus L, if I just have a box with some B minus L charge, I need to open the box and count how many baryons and leptons I have. There is no way to measure this charge from far away. Okay? So the point is that these global charges cannot be exact. They are only approximate, which means that in this particular case, for instance, there are two options. Either this symmetry is exact because it's actually gauged, so there should be some gauge field or gravity itself that is associated to it, so a new force, probably, that we have not measured yet. And the other option is that it's not exact, it's just approximate at low energies, but will be broken at some high energy scale. So for instance, the proton then will be expected to be unstable. Okay, so this is just one example. Let me give you motivation, okay, why this is the case, and then a more concrete example to show the power of this no global symmetry statement. Okay, so quickly the motivation is just that, okay, so let me give you some motivation with black holes. So the point is that black holes, they are like thermodynamic objects, so all you need to know right now, or believe me, is that they have some entropy, which is finite. And you can think of this entropy, roughly speaking, as what are the microsteps, like how many different ways you can construct the same black hole exterior, okay? Like from very far away, it looks the same. So like what is the information that is there? So if you construct a black hole with some charge, because for instance, you throw particles with different charges and so on, the point is that if the black hole is charged under a global symmetry, since I told you that these global symmetries cannot be detected from very far away, from outside, the black hole looks the same. Doesn't matter what is the global charge that it has. And this, roughly speaking, translates into being able to construct infinitely many black holes with different values of the global charge that still look the same and therefore give rise to an infinite entropy. Okay? So it violates entropy bounds. And this is a contradiction. Now, if the symmetry is gauged, you can measure it, and then you can distinguish the different values, and that's why there is no problem. Now, this is just an intuition. There is a way to make this more precise, but you should just take it as a heuristic motivation. The reason why we think this is a general principle of quantum gravity is because of the evidence that we have from quantum gravity completions. Okay, so in string theory, there is no global symmetry which is known. They are always broken or gauged. You can prove it in perturbative string theory. You can also prove it in area CFT for non-splittable symmetries using unitarity and locality of the CFT, like in holography. And also there was a lot of recent activity about understanding better the unitary black hole evaporation, using some topology changing processes and so on. Just so you know, the same tool that allows you to understand unitary black hole evaporation allows you to show that global symmetries are broken. Okay? So just as a comment, the way I think about this is that global symmetries are not well defined in quantum gravity, because to define a global symmetry, you need to have a fixed topology, and topology is something that changes in quantum gravity, in the same way that geometry changes in Einstein gravity. Just to give the comment here. Okay, anyway, so let me give you one example of a possible implication of this, and then I will go to the second constraint before finishing the talk. So one example, so this is the oldest and best understood conjecture, but in the past few years, there's been a lot of activity here, because there are new notions of symmetry that have appeared in the quantum field theory community, which have made us realize that this constraint can be more constraining than expected. Okay? So just to give you one example, if you combine the absence of global symmetries with anomaly cancellation and supersymmetry, just to give an example, you can rule out some supergravity theories by constraining the rank of the gauge group, meaning that you can say this gauge group, this theory with this gauge group cannot be consistent with quantum gravity, while this other gauge group can. Okay, so you're really constraining the possible landscape. And recently, in the past 3 years, I mean, this is very new, this has been used to classify the possible supergravities that you can have in dimension bigger, well, now even equal than 7, that are consistent with quantum gravity. Okay? So if we think that this no global symmetry is something general, not only from string theory, then you can use it to classify what are the possibilities. And surprisingly, or not surprisingly, depending on your taste, this classification that is done just using no global symmetries matches exactly the possible string theory constructions that you get from top down. Meaning that at least with this high level of supersymmetry and dimensions, you recover string universality in the sense that you are not missing anything, any possible theory, by studying string theory. And it's amazing that even with this level of supersymmetry, we can aim to answer these type of questions, okay? Like whether string theory is universal or not. Of course, here I have many dimensions, a lot of supersymmetry. What we would like to do next is to reduce the level of supersymmetry to connect with our universe. So with this message, let me try to reduce this level of supersymmetry. So if you want to use this conjecture for something more useful for us, you need to address, I mean, once you break supersymmetry, you need typically to address this question, which is, okay, you told me that symmetries are not exact, but how much they must be broken? Because that matters, no? What is the scale of breaking? So the rest of the constraints that I put in this map at the beginning, in a sense, are aiming to quantify this, like how much you can break these symmetries. They aim to quantify they aim to quantify the dynamics, okay, of the theory and what happens if you try to restore asymmetry. Okay, so then let me now focus on this second and last constraint. Let's see how much I time. 8 minutes. Okay, 8 minutes. Okay, so let's try to engineer an approximate global symmetry. Okay, so it's considered the space of parameters, and the point is that depending on the value of the parameters of your theory, you might be able to restore some symmetry. Okay, for instance, if you have a gauge coupling, if I make the gauge coupling very small, if I consider a very small gauge coupling, then I restore a U1 global symmetry. The symmetry is not gauged anymore, it's just global. So what happens then? Like how small the gauge coupling can be, because this is like having an approximate global symmetry. Okay, it's very difficult to answer this question in complete generality, but at least what we can do first is aim to understand what goes wrong from the perspective of string theory, okay, to see if it teaches us something. So in string theory, all these parameters, masses, couplings, and so on, are not free in the sense that they are parameterized by the expectation values of some scalar fields, okay, in the same way that the Higgs boson parameterizes the masses of the fermions. And these scalar fields is what determines the size and the shape of the extra dimensions and so on. But okay, what matters is that this parameter space is equivalent to the scalar field space in string theory. So it's a scalar manifold, has a metric defined by the kinetic term, and then moving in the parameter space is like moving in this field space. Okay, so we are changing the vacuum expectation value of the fields, and that gives rise to different theories with different values of the couplings. Okay, so what happens if we try to make, for instance, a gauge coupling which is very small in string theory? Well, what happens is that since there are no global symmetries in quantum gravity, what happens is that these points are pushed to infinite distance in this field space. They are pushed to the boundaries. Okay, so indeed, they cannot happen at a regular point. And not only that, when you take these limits, you approach these infinite distance limits, the effective field theory breaks down in a continuous way. Okay, so what is happening is that the more approximate, if you have a nearly exact global symmetry, the cutoff of the theory goes down, such that it goes to 0 when you restore the symmetry. But also, if you have an approximate symmetry, you can give some information about what is the maximum cutoff of the theory, what is the validity of the EFT. Okay. So what happens is that this cutoff goes to 0 because there are new physics, the new light states that appear and invalidate the theory. Okay, so this is parameterized by the distance conjecture that tells you when you go to infinite distance, you have not only one, but an infinite tower of states becoming light in terms of the distance. And this completely breaks down the effective field theory because you have infinitely many fields weakly coupled to Einstein gravity. So it gives an upper bound on the field range that you can accommodate within an EFT, okay, in terms of what is the cutoff. And also, so you know, if the tower is charged, so if I also have, as I was saying at the beginning, some gauge coupling that goes to 0, then what you get is a lower bound on the gauge coupling, okay, how weakly coupled a theory can be. Okay, so just to mention, I mean, most of the evidence for this comes from string theory, okay? Although recently we start to have also bottom-up arguments based on black hole physics. But it's an example of a feature which is very natural from a string theory perspective, like these towers are always there, it's like whenever you go to the infinite distance, but still surprising from EFT, because why you cannot have very weakly coupled theory, right? Like a very small gauge coupling or a very large field range. Okay, so just to finish the talk, let me give you one final example of an implication of this, which is based on a refinement of this statement, which occurs in the presence of a scalar potential. Okay, so if we have some potential for this scalar, what happens when you go to this infinite distance is that the potential goes to 0, like you have some runaway, in such a way that actually it also goes exponentially, so that the mass of the tower, of the new tower that appears, and the potential enjoy this polynomial relation. Okay, they are proportional to each other. Okay, so if you take this, okay, whenever you go to infinite distance, since the potential goes to 0 naturally, even if you don't have supersymmetry, and it's proportional to the light tower of states, you can ask, okay, can I make something useful with this? No? What are the implications of this for our universe? So a possible scenario is that the smallness of our vacuum energy, of the cosmological constant, is not due to some fine-tuning of contributions, but maybe it's a signal that we are near some asymptotic limit where the potential is going to go to 0 by quantum gravity. But then, if that's the case, I mean, this is a possible scenario, okay? If that's the case, and cosmological constant is small because of that, then there should also be a light tower of states, because you are going very far away, you are approaching these infinite distance boundaries. So what is the mass of this tower of states? So you can aim to constrain, no, what is to bound the mass. So let me just give you the result. From a theoretical perspective, you can put some bound on what is the relation between the mass of the tower and the potential based on what is called the Higuchi bound. So this comes from unitarity of higher spin fields in the zither. So it has to be from here to the right. And you can also try to put an upper bound coming from the Casimir contribution, like saying, OK, at least we expect to have quantum corrections from integrating out the tower, and they take this form, so you would expect this sort of behavior. Yes, I have just one more slide. So theoretically, you could aim to put this bound, and then you can say, OK, how this bound fits with our universe? Okay, because the cosmological constant is very small in our universe, so this scale is very, very low. Is it still consistent? Well, as I put here, surprisingly, it's still allowed marginally. Okay, so experimentally, you can put an upper bound, no, on what is the tower of states using astrophysical bounds and deviation from Newton's law, because you have an infinite tower of states. So that only if the mass is of order the potential to the 1/4. Oops, sorry, this didn't work. Okay, then you still have some hope, no, of having this scenario. So just this is the last slide. So the conclusion is that if we live in asymptotic limits, a possible scenario, you could try to explain why the cosmological constant is small, but then you should have the tower of states because of the these Swamplan constraints, which should have this mass scale, which is of order milli-electron volts. Okay, this is very light, which is actually the neutrino scale. Okay, so one can try to now make beyond standard models and see if, for instance, it can be a tower of right-handed neutrinos or what. And it's interesting that what is interesting that from quantum gravity, I mean, from this Swamplan constraints, you get this correlation. Okay, you are correlating the mass of some tower, like for instance, neutrino scale, with the cosmological constant, which in principle are disconnected. And then you can show, I mean, I don't have time to explain, but you can also show that this tower, you could ask, okay, what is the meaning of the tower? And using both theoretical and experimental bounds, you can also constrain that the only possibility that is still consistent with our universe would be only one extra dimension, okay? Which is what we call the dark dimension. Okay, so let me conclude. So I gave you 2 examples of these quantum gravity constraints. No global symmetries and the distance conjecture, which are very motivated from string theory and black holes. And I give you 2 examples. One of them is a very robust example in which you can just use no global symmetries to classify the possible landscape of supersymmetric higher dimensional theories, hopefully reducing the level of supersymmetry in the following years. The other one is an scenario, which is motivated by these Swamplan constraints. So it's not necessary, it's a scenario, but serves as a proof of principle of how these constraints can give some useful phenomenological implication and can change this logic of naturalness by implying non-trivial correlations between the different parameters of the EFT. So with this, let me thank you for your attention and just tell you that if you are interested in the Swamplan, we organize this online series of seminars every Monday, and everybody is welcome to join.
So thank you very much, Irene, for providing us with some keys to distinguish Swamplan theories from landscape ones. Okay, questions?
What is the agent responsible for the breaking this symmetry?
Depending on which one. So you can think that there is a minimal breaking, okay, that you can try to associate actually to black hole physics. That, I mean, at the very least, the existence of black holes in your theory will break the symmetry, and then you can think that this appears as instantonic effects, like gravitational instantons. And this is like the minimal breaking that you are going to have. But in practice, when you study concrete models in string theory, for instance, sometimes you get that the breaking is much higher. So it's not just only about gravitational instantons, but things get correlated to each other so that you can have a perturbative breaking, and it can also be about the cage theory, like different things. So it really depends on the particular example, what is the source.
Any other question? Okay.
How much can you say from these conjectures about the properties of this tower of states? I mean, for instance, can you say something about the spacing of the tower and the degeneracies at each level? Because this is very important for phenomenology.
Yes. Yeah, so I didn't go into these details, but for sure you can say that it's weakly coupled in the sense that the notion of this tower of states is that there is like a new weakly coupled description of the theory. So they are weakly coupled to Einstein gravity and so on, so it's like a weak coupling limit. And then about the spacing and so on, there is no general argument from bottom up about what could be. What we have done is to classify the possibilities we have seen so far. So, I mean, it would be amazing. I mean, it's an open question to have a more general argument about the possibilities. But from gathering data from string theory, so far, the only 2 possibilities that are known is that it's either kind of a decompactification limit, like a Lusa-Klein tower, so it's equally spaced, or it's a string tower, like the string modes. And even from string theory going to very weird limits and so on, we have not been able to find even a tower from a membrane or from different objects. So we see either a string or a keiki tower. Why is that? We don't know yet. It would be nice to find out.
Okay, thank you. There was one question here.
Yeah. Well, in the case that gravity turned out not to be fundamental, and therefore gravitons wouldn't exist, you think still would be anything left or a lot left of the scenario, the swampland ideas and landscape ideas?
I guess it depends what is replacing it. I mean, what would be the completion, but the expectation here is that we are trying to, we are trying to understand what are the minimal consistency requirements to have a description of gravity at the quantum level, whatever it is, right? So if you tell me it appears from other things, maybe these constraints it means that this constraint can also be obtained from other, I don't know, only gauge fields or other things. So maybe there is a way to understand also these constraints as composite or more complicated versions of other simple things. But the goal here is try to understand the rules of the game, whatever they are. Now, so far, the big laboratory that we have for this is string theory. So many constraints are very motivated from string theory, and it's a very interesting question to understand which ones maybe are specific of string theory or are completely general. And this is part of the question that we are trying to understand. And that's why it's very important to gather evidence, not only from string theory, but also thinking of black hole physics and other things. But it's part of the question.
Hi, Irene. Thanks for the nice talk. So I have two curiosities actually related. So in this swampland landscape, is this something binary, or there is a notion of the instance of how, if you are in the swampland, how far are you from the landscape? So or it's basically you are bad or good. And maybe related to that, how much can you say about the standard model? So can you say something if the standard model is in the swampland? I mean, the model as we know it.
I guess maybe you can try to formulate a kind of distance using the cutoff, in the sense that sometimes it's not binary in the sense, I mean, maybe with global symmetry you can say, okay, either you have it or not, but most of the constraints is more like, okay, this effective field theory is okay as long as it's valid below a certain energy scale. If you try to go above that, it must drastically change. Like you cannot claim that the theory is above that. And this cutoff tends to be much below the Planck scale. Like it can be much below. So how below? Maybe you can use it as sort of a distance. Like, okay, this effective field theory is fine, but this is nearly being ruled out because I'm using it at an energy scale which should be very close to the cutoff. Like if I have a very weakly coupled dark photon, it's fine, but the cutoff is going to be proportional to the gauge coupling. So if I use this for a TV scale, I have to check if it's valid or not, and maybe it's nearly. So it depends what we want to use. In that sense, the standard model, so far, just without taking into account neutrino masses and other things, just like the standard model, there is no, like the electromagnetism satisfies this by a lot. So there is, I mean, it's really like deep into the landscape. But once we start adding beyond the standard model things to explain some of the puzzles, then it's very easy to get to the boundaries and be close to being ruled out.
Okay, last question, and then next speaker, please get ready.
Thank you very much for the very nice and comprehensive talk. I was following also the same comment, is if you can already disprove some of the BSM extension that you can probe at experiments and you can guide which ones are more interesting than other ones?
Yeah. So there has been, I mean, I could just give 2 examples, but there has been a lot of literature about this. And there are examples of theory that have already been ruled out in this sense. Like, for instance, I mean, this started especially with inflation. Like when you have, I mean, whenever you have like large field ranges or small gauge couplings, then this becomes more interesting, and then you can aim to rule out some theories. So there were some relaxation models of the electroweak hierarchy that have a very large field range, which would not be compatible with the cutoff that they need. Also some models of inflation, not all of them, but some models. And from beyond the standard model, also like dark photons, you can also constrain how light the dark photon can be, and then like put a constraint, a bound on the couplings. So yeah, I mean, there are many, I mean, if you are interested, you can also, I mean, there are some reviews and lectures that you can find some references, but that's why we are interested in, no? Like, because we can aim to constrain it, and the goal is try to make this precise enough so that we can trust, no, these sharp bounds, because that's the hard part, no? Like when you try to make it, like qualitatively everything is more clear, but now what we want is to give a clear, sharp bound of what is allowed and what is not, and that's where the bulk of the work is going, no? Like try to make it precise.
Okay. So thank you very much, Irene. I think we all feel invited to these seminars and discussions. And now we turn to the next speaker. Okay. El tuyo era el PPT, ¿no?
¿Perdón?
Que el tuyo era el PPT.
Sí, justo.
¿Te funciona? ¿Tienes ya?
Creo que me van a dar esto y sí, esto creo que funciona.
¿Te lo habilito? No hace falta.
Sí. Y ahora...
Póntelo en pantalla completa. Okay. So now we go to the deep waters, and we have Juan de Zornoza from IFIC and Universidad de Valencia, who will tell us about neutrinos at the Mediterranean.
Okay.
So, whenever you wish.
Sorry. Thank you very much. I would like, first of all, of course, thank you, the organizers, for the opportunity of being here, to talk to you about the neutrinos at the Mediterranean, past, present, and future. And as you will see, it's a special moment for our community because, as I will show you, we are now in the year of closing Antares. In any case, you can see there is a lot of future, and this is one of the things one of the messages I will try to convey. This is just the cover of the last issue of Sun Courier. So yeah, let's see. So this is an outline of my talk. So yeah, at the end of the day, I want to send 3 messages. We will have one sad note, as that I already mentioned. The fact that we are closing Antares. But yeah, at the same time, we have 2 happy messages that I will also try to show you. So yeah, this is the overlay. So I will just make a brief introduction to the kind of science and how we can do it. Neutron astronomy, and then I will make a summary of the Antares history. This epoch is ending, so there will be some kind of remember session. And then I will show you which is the status of CPAN, okay, and the prospects. And then I will go to the main part of the talk, which will be to discuss about the physics results and also the prospects that we have for CPAN. Okay, so. Let's start with, as promised, just an introduction. So, first of all, a reminder that the raison d'être for these detectors, for neutrino telescopes, is to observe the universe in a new way, okay, with neutrinos. And this is very interesting because, well, as you can see here, of course, we have been observing the universe with photons and also cosmic rays, for many years. But now we also have the opportunity of using a new messenger, okay? As a matter of fact, too, because we also have now, gravitational waves, okay? But, the thing is that, we can observe the universe in particular, or these detectors are very useful to look at the universe in the high energy part, okay? These high energy neutrinos will bring us information for events, for astrophysical objects, which are very catastrophic, in a very extreme, conditions. So there is a lot of fundamental physics that we can also learn from these events because of these extreme conditions. And of course, also trying to understand, these very catastrophic, very spectacular objects. Okay, and this is something that in particular, for far away, photons, are not, cannot help us that much because they are absorbed. Okay, Of course, I mean, we have this complementarity, but yeah, I mean, this is, I mean, where, I mean, we want to look at the universe. But as I will comment, I mean, in addition to this astrophysical side, we also, I mean, have this beam of atmospheric neutrinos that is also very useful, I mean, for studying neutrinos. So, just to start on the thing, I mean, let me just, I mean, show you a selection of some more or less recent results from our, let's say, I mean, trailblazer IceCube, which is a spectacular detector. So, for instance, I mean, here I have made a selection of, I mean, things related to astrophysics, but I mean, as you may know, I mean, also they have been producing also results related to, let's say, particle physics. But anyway, I mean, let me just comment about this selection. For instance, I mean, something like 10 years ago, I mean, there was this announcement of the observation for the first time of this astrophysical diffuse flux of cosmic neutrinos, okay, at high energies. And this was very important. Okay, this is, I mean, at that time, this was 5 sigma. Now they are, more than 8 sigmas or whatever. So, and this is again, I mean, a diffuse flux. Okay, we are not, we observe this as a not from specific sources of the specific places in the sky, but just as a diffuse flux. Okay, but it was clearly above the background. And also, I mean, when you calculate which is the associated flux, you realize that this is high. I mean, Sergio Alves, I mean, our student, I mean, was in the Renata session, was showing this plot comparing the fluxes, or I mean, multiplied by the energy square, which gives us, I mean, a kind of idea of the energy in the universe in these probes. And there was this comparison between gamma rays, neutrinos, and high energy cosmic rays. And the level of energy in the universe in the three messengers is more or less the same, okay? So the universe is full of neutrinos. Then, I mean, something like 4 years ago, I mean, we had this announcement, I mean, of this alert of high neutrinos that were sent to, well, I mean, as usually done, I mean, by IceCube and also by Antares, to several detectors, and it was observed this correlation with a flare of a blazar. Okay, just I mean for the for the people from the caverns, let's say. I mean, a blazar is one of these is a kind of AGN, that is, I mean, one of these supermassive, I mean, a galaxy with a supermassive black hole in the core, where there is accretion of matter. So you have these jets with acceleration of particles. So if one of the jets is pointing towards us, we call it blazar. Okay. So in one of these sources, I mean, it was just in a period where this blazar was flaring, as seen in gamma rays already and so on. So well, I mean, it was, I mean, an evidence of the first, let's say, I mean, point source source of neutrinos. And also very recently, just something like, I mean, 2 weeks ago, I mean, we had this announcement by IceCube of the observation of, again, this NG thing is a AGN. In this case, is observed, I mean, from the side. And in this case, it's a steady source. Okay, this is a source not like this one, which was observed in like a peak of neutrinos. In this case, it was observed, I mean, after analyzing many data and seeing that, I mean, there is an excess here. Okay, so yeah, it's very, very active, I mean, these things. So how can we do these things? So our, let's say, golden channel would be, I mean, muon neutrinos interacting charged current in the water or in the ice, and then they will produce a muon that will, induce, I mean, Cherenkov light that we can detect with an array of photomultipliers. Okay, so we have, I mean, many of these balls, I mean, in the water or in the ice, and with that we can, well, I mean, reconstruct, I mean, quite well, I mean, the direction of this muon, and therefore that of the neutrino. Okay, and and for reasons I don't have the time to discuss, I mean, it's places like the ocean or a lake or the Antarctic ice the most appropriate for that. Okay, because we need, I mean, huge volumes for doing this. This, as I said, I mean, this is our golden channel. Okay, this is just, I mean, as how it will be seen in Chem3Net, I mean, in ARC in particular. So, you see, I mean, these are long tracks whose direction is going to be easy to reconstruct. But we also have this other channel, I mean, coming from neutral currents or cis interaction of electron neutrinos or tau neutrinos, which, well, I mean, are seen more as a bright sphere of light. Okay, so in this case, I mean, the direction is not so easy to reconstruct. Also, as I will show you, I mean, in the water is still good. But anyway, okay, so this is how, I mean, our, our main channels. so this is how our signal would be, but we have also to deal with backgrounds. Okay? In particular, I mean, our main backgrounds will be the atmospheric muons produced by cosmic rays interacting in the atmosphere. So we have to put the detector deep in the water, and also, and very important for some of the discussion I will make later. So this background is huge, of course, in the downward direction, but for upward, I mean, the Earth, I mean, filters, I mean, most of these muons. Okay, so we can select, I mean, only upgoing events as a way, I mean, to remove, I mean, most of this huge background of atmospheric muons. We also have atmospheric neutrinos, also producing this interaction of cosmic rays in the atmosphere. And well, I mean, to fight with that, you have to, well, for instance, I mean, to use the fact that we expect, I mean, these cosmic neutrinos, I mean, to be of higher energies. This is, for instance, what it is done in this diffuse analysis I mentioned before of IceCube. Or, of course, I mean, you can use the fact that, I mean, if you're looking for point sources, so you will look for concentrations in the sky, or also, I mean, time concentration of your events. Okay, so you have two ways to deal with that. Okay, and also remember that, well, I mean, this is background, okay, but as I mentioned at the very beginning, I mean, these atmospheric neutrinos are also a free beam of neutrinos with, well, I mean, with which we can do a lot of physics. Okay, so what can we do with neutrino telescopes? Well, I mean, we can do many things, and this is one of the nice things of these detectors. I mean, there are a wide variety. So, of course, I mean, let's say, I mean, the main goal would be, I mean, to study these astrophysical neutrinos. But we can also, I mean, look for dark matter, as I will show you. We can try to learn about neutrinos themselves, and well, I mean, we will also discuss on that. And even we can try to, for instance, I mean, look for things like a supernova. Although they are, you know, not the main goal, but we can do that as we will see, and many other things. Okay, and we will discuss, I mean, some of them. As you can see, I mean, depends very much. I mean, depending on the topic of physics, I mean, you will go to different energies, and this is also related to well, I mean, to how the detector is designed, of course. So here, yes, I mean, to have a comparison between the main detectors I'm going to comment today. So you have here, for instance, Antares, which would be something, you know, medium. Of course, I mean, here you always have this trade-off between size, you know, which will give you access to very low fluxes. In particular, this means, I mean, to access to fluxes at very high energies. So if you want to detect these fluxes, I mean, you need something big, but of course then you cannot instrument your detector, I mean, very densely, right? So, and the price to pay is just to have, I mean, a higher energy threshold, okay? So this is what you have, for instance, in IceCube or in Chem3net ARCA, okay? ARCA is the large version of Chem3net. But we can also go the other way around. I mean, we can also go to a denser detector, but then, of course, I mean, you have to build it, I mean, smaller, okay? But this is the idea behind Chem3net ORCA, okay? So you can see, I mean, here we have a threshold which is low, I mean, so that we can study neutrino oscillations, okay? Of course, I mean, here small is relative, right? I mean, you can compare, I mean, ORCA is huge compared to Super K, okay? But of course, I mean, Super K has an even, I mean, a smaller energy threshold. So yeah, there is, so there will be complementarity between the things that we can study between the different detectors. So let me show you, I mean, a comparison. I mean, I'm coming back, I mean, to this thing of the you know, I mean, the propagation of this Cherenkov light in the water. I'm going to show you a comparison between how light propagates in ice and in water. Okay, yes, also to keep in mind comparison between IceCube and Antares or Chem3net. So in the simulation I'm going to show you, you will see a shower, one of these showers. I mean, in both media, and here the colors will be that green, blue means light more scattered, while red means, you know, light more direct, okay? And this is very important. I mean, to have direct light means, I mean, not scatter. It's important in order to keep the information of the, you know, of the event, so that you can reconstruct well the direction in particular, okay? And also the energy. So, for instance, yeah, this is in the ice, and this is in the water, okay? In the Mediterranean. So you see, I mean, very soon here you have, I mean, things which are blue, green, meaning that, you know, all these photons have scattered. Okay, while in the sea, in the water, I mean, you have, I mean, you know, you keep this information. Okay, and we will see the consequences of this in a minute. Okay, so first let me just, well, I mean, remind you about Antares. So it's, well, I mean, 12 lines. It was completed in 2008, installed in the, you know, close to Toulon in the Mediterranean Sea. And this news is that well, we closed, so we gather all the lines of Antares just a few months ago. Okay, after 14 years of operation, which has allowed us to have, a very rich scientific harvest, as I will show you. But in addition to these, scientific results, it's also important, to insist that, we have also learned how to, be efficient, doing neutrino astronomy under the sea. It has been, a proof of concept for undersea neutrino astronomy, which, is not easy, at all. It's, the sea is very aggressive, okay, but we managed to do that, and we learn a lot in the meantime. So, so we have now Antares, somewhere in Marseille, and some of these elements will be brought to the laboratories for exhibition. Well, so this is, this is just, to review, very quickly, the history of Spain at Antares. So the collaboration itself was born in 1996, and just 1 year after, IFIC joined. As a matter of fact, after a proposal by Manuel Aguilar, so to Juan Hernandez. So this is how we started. And then, other groups, other Spanish groups joined. Okay, until we have, the commissioning. So along, a lot of things have passed in the meantime in these 25 years. So by the way, we are not any. You have nothing to do with this 23 under suspicion. Anyway, so in these 25 years, we have done, many things. Many things have changed. This is just a comparison between the very old times. Some guys have not changed that much. But one of the things that has changed is the size of the group. We have, more groups. And also, with more people. And here, let me also, take advantage of this opportunity that Juanjo Hernandez is not here, to get embarrassed. To underline, his role, as a leader and as the head and the heart of this project. He's still very active. So, I think this is something that has to be underlined. But of course, many people, have been doing things here from Spain. Installing the detector, taking data, analyzing data, even playing the Petrolari, as you can see here. Sergio with these OM balls. Okay, good. So, by the way, there is this review, a recent review, where we, kind of summarize, all these things where we contributed. But you can see here the list, and I will review some of these topics in a moment. So, this includes, construction, also analysis on astronomy, dark matter, neutrino properties, acoustics. Okay, and this is, this is one of these, happy messages. So, the things we did, included from, characterization of photomultiplier. This is how I started, so imagine it's a long time ago. And also things like, optimizing, working on the optimization of the layout of the detector. This was, before having the detector, built. We were working on how to, which was the optimal design. This was also done here at IFIC. We also work a lot on what we call the optical beacons. These devices, to emit light so that we can proceed with time calibration and study of optical properties. So we designed and built this laser beacon, these LED beacons that there are in many lines. And now we are also continuing this work, working in these so-called nano beacons, which have a similar function, but now, installing each of the optical modules. So this has been one of our priorities, in the hardware and also in the analysis. Also, for instance, we did, at IFIC, we did the first neutrino sky map. This is Paco Sales's thesis. So of course, only noise here. But this has been, one of our main topics. And we have, several papers, of which we have been in charge on this topic, which is, of course, having the neutrino sky map is one of the main results in these detectors. Okay, now let me move, to ChemTreeNet. So, which is mainly a European collaboration, but as you can see, we have also groups from Australia, South Africa, even China. So, as I said, we have ARCA, which is this large version, like an ice cube, close to Sicily, 1 cubic kilometer, and then we have ORCA close to Marseille, close to where Antares was. Okay. So some data about the status of the detector. Well, first, so these are the, let's say, the number of lines and things like that. So one of the nice things of, there are two configurations, but the technology is the same for ARCA and for ORCA, okay? Which is very advantageous in terms of, logistics and, construction and all these things. This is quite nice. So at the end of the day, the difference is mainly the length of the cables and the distance between lines, okay? And you can see that here, where I put, some numbers, okay? So ORCA also has, it has more lines. this is what we call, 2 building blocks. More than 200 lines, and for ORCA we'll have 1 building block. This is 100 lines. Okay, but the lines are very similar. It's just as I said. The difference in the length of the lines. So which is the status now? Is the following. For ARCA we have now more than 20 lines, and for ORCA we have more than 11 lines. Remember that Antares had 12 lines, and each of these lines is much more than one Antares line. We have this. You can see here this picture. We changed the design. We moved from having a large photomultiplier to several, actually 31 small photomultipliers in each optical module, okay? So this gives us, much more, detection surface. Okay, so this is, one of these lines is much more than one Antares line. Anyway, so, and by the way, some of the results I'm going to present from ARCA and ORCA are with, data from 6 lines that are already analyzed, and we are also doing more things. And also let me point out that in 1 year, a bit more than 1 year, and we'll have in total more than 60 lines between ARCA and ORCA. Anyway, one of the nice things of these detectors is that you don't have to wait until, putting the last scroll. Once you have, a few lines, you can start, doing physics, okay? Which is now, okay, as I will show you. Okay, now we have, we are taking data, and we are analyzing this data, to produce results. Okay, yeah, this is another good thing. So, yes, some pictures of this installation. We have, these lines, rolled, and inside of this kind of cage that we put into water, and then it's open, and then unrolls, and there we have, the line that we have to connect, and with a robotic submarine, it takes the cable and then put it in the water. It's not trivial, all these operations, but yeah, you have experience, as I mentioned. And yeah, and we have data. This is a simulation of not a simulation. This is a Antares, ORCA data. This is ORCA 11. So you can see a couple of examples of events, seen in the detector. Okay. So you can see, first seen in the lower part, then seen in the upper part. So this has to be a neutrino. Okay. Cosmic or not, probably atmospheric, but we are seeing neutrinos already with these detectors. Okay, so let's go to the physics results. There is some, first of all, this is just a selection, and it's with some, bias towards IFIC results also. Not everything will be IFIC. So let me start, for instance, with astronomy. So, well, with Antares, for instance, one thing we can try to do is to look for a diffuse flux, okay? That is, to look for the sum of the fluxes of all cosmic sources of neutrinos in the universe, okay? So here there is no directional information, let's say. Just, we are looking for the sum, as for instance, this Hesse analysis, okay? This is the first analysis I mentioned before of IceCube, okay? So here, basically, since you don't have this time information or spatial information, what you can do in order to select your signal is to put a cut in the energy, as I mentioned before, and try to look for an excess in this part here, okay? This is trucks, this is showers. So Antares is small, okay? So we cannot, we couldn't see, this IceCube flux, but what we see is an excess with a value which is, compatible with what IceCube is seeing, okay? So we have not, enough data, let's say, to claim a discovery on our side, but clearly what we are seeing looks like, the IceCube, we are seeing, the IceCube flux, okay? And this is, the parameters of the flux that is typically parameterized like this one, a power law with a normalization and a spectral index, okay? So, yeah, almost 2 sigmas, but not bad. And we can also try to do this with ARCA, okay? As I said, in this case, ARCA 6, that is, with 6 lines. So, of course, here, we are not competitive with Antares or IceCube, but still, at least, this just, allows us to show that, things are understood, when we compare data in Monte Carlo, and, well, that all the machinery is in place, okay? But, well, no high energy has been observed as expected, as a matter of fact. Let me come back to Antares to show you, this very recent, this is just like, presented this week, to the external world, analysis on the galactic reach, okay? So in this case, what we are looking is to the region of the galactic center, which is, the central part of the galactic plane, okay? Remember, and I will insist on that later, that because, if you want to look if you want to observe our galaxy, and in particular the galactic center, it's much better to be in the north, okay? Because of this thing of using the Earth in order to filter, this huge background of dangle atmospheric muons, okay? So from to observe the galaxy well, you have to be in the north, okay? Okay, like Antares or Kentnet. So. So this means, in order to observe this galactic reach, it's much better, to use, for instance, Antares. So these last results show, still, can exclude at the level at 95% confidence level the absence of any signal there. Okay, we can exclude just the only background hypothesis at a good level of confidence level. Okay, of course it's not a discovery. Antares is small, but it starts to look. There are hints there, which, by the way, this is what we expect. When we make a fit, models predict that well. You have there gas, so you expect cosmic rays to be interacting there. So it's at the level of the signal that you were expecting. Okay, so and there are rumors that IceCube is also, seeing something there. Okay, so it's starting to be very, very interesting. Of course, we can also look for point sources. Okay, and yeah, this is just typically for this analysis you can just look in the whole sky. Okay, and look for an excess, and this is shown here. No excess. Or you can also look at specific places, places meaning, where you have, an interesting gamma source or a IceCube hotspot, things like that, okay? So, yeah, this is just, a summary. For instance, this is the most significant source. I will comment on that later. Nothing of this is significant, okay? But this is still intriguing. Well, apart from this, that I will comment in a minute, that the second most significant source is just this Texas. This is the second source I mentioned in the introduction of IceCube. Okay, so I have to speed up a bit. But for instance, this is the most significant source in the Antares point source analysis. So it is very interesting. Also, it is not significant. That well, we have, when looking at the time information of these events, it seems that there is also in correlation with this Antares event, there is also, an event of IceCube, and also some activity as seen by, in radio and Fermilab in that direction. Okay, this is also one of these AGNs. Okay, and yeah, and we can also try to look for point sources with with ARCA, but again, it's small, so the limits are not competitive. It's also very important, to check our alignment, okay? Because we don't have like Abelardo was showing the other day. A standard candle like the crab, okay? For neutrinos, what we do is to try to look for the shadow of cosmic rays due to the sun or the moon, okay? And we can, we can try to look if the moon or the sun are what they are expecting, and also with the shape. And and things are in order, okay? So we rely on the absolute alignment and also on the angular resolution that we think we have. Okay, and which is summarized here. Look at this. This is 0.1 degree. We have at high energies. For muons, we have a very, very good angular resolution, and also for showers, it's just 1 degree. Okay, at high energies. Remember, Amanda for tracks had 2 degrees. Okay, and it's very important. The angular resolution, as you can imagine. For instance, in this last source, in this third analysis I show of IceCube. This source was there from the very beginning, of course. So, the fact that they discovered it now was in part because, they had more data, but also because they improved the analysis to have a better angular resolution, and then the source appeared, okay, with significance enough. Okay, I have to hurry up a bit. Let me also mention that, we have all this online program to receive alerts, also to send alerts, which is very important in this new multi-messenger era, just to have, more information about the sources, to understand better the models, but also, to take advantage, to have the opportunities to see ourselves, and also to let other observatories to see some things that, they would miss. Antares, these detectors have full sky coverage all the time, okay? And this is very convenient for these transient searches. So, I mean, I don't have the time to comment, but we have, for instance, I mean, we have search for correlations with the gravitational wave events. We also have sensitivity to supernova. I mean, basically any supernova in our galaxy, we will detect it. And we have already integrated, I mean, we are already integrated in this S-News system. And now moving to dark matter, let me mention that, well, I mean, we have analysis for several sources. At IFIC, I mean, it has been one of our major contributions. We have analysis on the sun and also on the galactic center. And also the groups of Gandia and Granada are contributing to this. So for instance, just an example, I mean, we have, these limits for our searches in the galactic center. Remember, I mean, from the north is the place, I mean, to look well at the galactic center. And this allows us, I mean, to have, I mean, limits which are, in particular at high masses, much better than what IceCube, I mean, can constrain, okay? And now we are also, calculating sensitivities for ARCA, for instance, okay? And also analyzing data. And and also have results for the sun. I mean, for the sun here, Antares cannot compete with IceCube. But let me insist. I mean, neutrino telescopes. I mean, are in order to constrain the spin-dependent cross-section, are the best tools. I mean, because the sun is a huge target of protons, right? So it turns out that IceCube is putting the best limits, and of course, Orca and ARCA will also have an important role. And one of the nice things of this analysis, these searches in the sun, is that we don't have astrophysical backgrounds. I mean, we see a signal of high-energy neutrinos, so it has to be dark matter, or something even more exotic. Okay, and let me finish the last part concerning neutrino properties, saying that, we have, as I said, for us, we have these atmospheric neutrinos as our beam, which means that, we have, high statistics. We have also typically, high energies compared with other detectors. We have also, of course, baselines, up to wide, and also, long baselines up to the diameter of the Earth. And, well, several flavors, and also, some of the neutrinos will traverse, a very dense part of the Earth. So, let me just mention that, with Antares could see oscillations, okay? But of course, not with a good accuracy. But with Orca, just 1 year, we can see very well, these oscillations, okay? We have, already results that, well, are okay. But, with full Orca, we'll have, very good results, constraining the atmospheric oscillation parameters. But the main goal of Orca is not that, is to look for, try to measure the neutrino mass ordering. And, well, you can see this here summarized. So, depending on the ordering, we can have, more or less sensitivity. But, a recent work that is very interesting is the fact that when we combine, the results from Orca and Juno, which is also now been finished, so then things are very powerful. You can see here, even independently on the mass ordering, we can have, a measurement of this in 6 years because of how they complement. And we can do other things, and things that we are doing at IFIC, for instance, and we can try to look for neutrino non-standard interactions. So, for instance, we have done this for Antares, and we got, results which have been recently published, which are among the most restrictive ones to date. Okay, this is nice. We didn't see, these non-standard interactions, but these detectors are powerful for these things. Or, sorry. And of course, we can also try to do that with ARCA 6, or of course, even better, we will do that with full Orca, and then we will have, very good results. And the final thing I want to show is these results on the neutrino decay as another example of early physics related to neutrino properties that we can do already, with Orca in this case, okay? So again, as in the previous case, what you look at are distortions in the oscillation spectrum. So, for instance, in this case, for these models, we can have, limits, lower limits on this parameter, for instance, this inverse of the alpha 3. Which, of course, with Chem3net Orca will be much better. Orders of magnitude better than present results. So I think I have to finish. So this is my summary. So yeah, the message. We can do many things. Both in the side of astroparticles and also particle physics. Antares has shown, many physical results, but also the feasibility of doing these things in the water. And now we have Chem3net. Already with many lines. More. Will be deployed soon. So yeah, exciting times ahead. So thank you very much.
Okay, thank you very much. So 1, 2 questions. So there is one there, Pilar.
Yes, thank you for this overview. For the PMTs, what is the difference between Orca, Arca, and Antares?
So, I mean, for Orca and Arca, it's the same. As I said, I mean, one of the nice things is that, I mean, they are exactly having the same technology, so it's just the same. So the difference is that in Antares, as for instance, also done in IceCube, so it was used, I mean, a large photocathode photomultiplier, right? I mean, it was just one big photomultiplier in each optical module. In Chem3net, and this is something that is also being copied, let's say, I mean, by the ideas, I mean, for upgrading IceCube. I mean, the idea is that using, I mean, this what we call, I mean, multi-PNT DOM, okay? So we have 31 small photomultipliers, and this has the advantage, I mean, this has, I mean, several advantages. For instance, I mean, you can reject, I mean, better, I mean, the noise, or in particular also in the water. But at the end, is, I think it's thinking like having, I mean, a camera with more pixels, no? Because we have, I mean, 31, and also we have, I mean, coverage of the whole in 4 pi almost, okay, which is also very advantageous. So yeah, this is the idea. And as I said, I mean, also, I mean, IceCube, I mean, for these upgrades is considering, I mean, also this idea, very similar.
Okay, thank you. One very last fast question.
In this experiment, in general, one can distinguish between neutrinos and antineutrinos?
No. Well, I mean, statistically, I mean, thanks to the Bjorken variable, I mean, you can, I mean, compare distributions and try to have some information. But we don't have, I mean, a magnet or anything. So it's just, I mean, we have some handle on the flavor, but not on the sign, let's say, of the neutrinos, except of this. I mean, that is being studied. I mean, the light distribution can have some differences, but they are not very big. I mean, you see that at the end, I mean, just accumulating the statistics.
Okay, so let's thank Juan again. Okay, so now we turn to Javier Cuevas from Universidad de Oviedo, who is going to talk us about Higgs physics, the road to the discovery and the way we are understanding it. So thank you, Javier.
Thank you, Begoña. Can you hear me well? Okay, so thank you, the organizers. Thank you also all the colleagues that provided me information on the different activities in the different groups in Atlas and CMS that I am going to present today. Well, my first word is about this search first for the Higgs, then the discovery, and then the measurement of the properties is a truly worldwide effort. And of course, many communities are contributing to the effort. First, of course, is the LHC, is the accelerator. It's performing very, very well since the beginning, since 2010 until 2018. And you have heard this morning, Aurelio, that it's working perfectly well at 13.6 TeV starting this year. Of course, the second part is the detectors. The detectors are working very, very, very well. There have been a lot of effort by the community during the last 30 years to build the detectors that were able to make the discovery of the particle. We cannot forget about the computing. The computing is an integral part of all the effort. You heard 2 days ago, Antonio and others on which is the performance of the computing in in the LHC era, and everything is working well, and of course, the theory. And the theory has been progressing very well in providing cross-section of the, not only on the Higgs production, but also on the backgrounds and Monte Carlo improvement and all that. So, you know very well that the discovery was done in 2012, and the first thing I wanted to say by the Atlas and CMS. So what Atlas does, CMS confirm, and was what CMS does, Atlas confirm. And this has been basically all the time. So all the time we are collaborating, we are competing, we are in some sense, we are sometimes we make some effort to combine some results. Up to now, we have many results on Higgs and other things. And one important thing is that, of course, we make the Spanish groups made a lot of contributions to this discovery. From the fundamental point of view, you know very well that this discovery is well identify a mechanism for the mass generation for the particles. And of course, it's a new sector on the Standard Model that we are starting to study, the Yukawa couplings, the gauge-boson interactions with the Higgs, the parameters of the Higgs potential, and all that. Another important thing is that apart from the direct observation of the Higgs, there is no direct observation of any other new physics at LHC. So that's why it's clear that the Higgs is, in some sense, driving all the future of the high energy physics, and we need to make a precise measurement of this particle, and this is basically the program of this thing. First, of course, we need to measure the cross-section, the branching fractions. We have to make these measurements not only inclusive but also differential. This STXS is a way in which these measurements are presented in different bins of different distributions of the particle. Of course, we need to continue measuring the mass, the spin, the width. The width is a new measurement that is appearing this year, probably, with the data of the run 2 of the LHC, the couplings to fermions and to the top quark. Of course, one important thing is that appears in the analysis of the full run 2 data is the couplings to the second generation. We are starting to see couplings to muons, not only to muons, but also to the charm quark. And well, the hot topic probably for the run 3 and for the high Lumi is the self-interaction, the production of di-Higgs and all that. And of course, we will keep making another searches for more Higgses, for couplings of the Higgs to the dark matter, to other type of matter or whatever. So, well, this is just to remind you that about the day in which the discovery of the particle was presented 10 years ago. And, well, I would like to stress again that both Atlas and CMS were present in this presentation. And thanks to the contribution of the two collaborations and of the contribution of many channels that I will show you a bit later, we can claim a discovery, a clear discovery of a new particle. And well, it's clear that this led to some consequences. Well, some historic view is that this is a way in which, traditionally at LHC, we have used the statistics, the statistics tools, and well, in summer 2011, we started to see something around here, both CMS and Atlas, not very precise, but at the end of 2011, we started to see basically the same thing at the same mass. And, this, let's say, a small bump led to take one of the first difficult decisions at LHC, that was the continuation of the program or the operation of the accelerator in 2012. This was a difficult decision because they imply some risk in the accelerator, but in any case, the decision was, one can say that it was the good one, and in 2012, the LHC was continuing giving us data. And at the time of July and the time of the 4th of July of our ICHEP, we started to see something in common, and 125 GB. And this is the time in which the new particle, we claim that we discovered a new particle. Then we continue taking data, and we start, of course, this confirms the first observation. And, well, this combined p-value started to become basically irrelevant. So we at the end of 2012, started to measure the properties of this new particle. Well, of course, you know very well that in 2013, these guys received the Nobel Prize because his, of course, contributions to the understanding of the origin of the mass of these particles. And I would like to underline that also ATLAS, CMS, the CERN, and the LHC were mentioned in the Nobel Prize. Okay, so the LHC discovered the particle, but the roadmap was starting much earlier. I would say that this is a good point to consider that the thing started from the point of view of the experiment. You know that in this paper and some continuation of this, John Ellis and others started to compute cross-sections, started to compute branching ratios and all that. That is the thing that we need to look for new particle at LHC or whatever. But remember these things that at the beginning, well, it was not so clear when and how this could be realized. So LEP was, as you know, was running for 10 years from 1989 to 2000, and there is many legacy many legacy results from LEP, but related to Higgs, the most important one is that after looking for this particle up to the highest possible energies at LEP of 206.5, but we have 10 minutes at that energy. But in any case, it was clear that at least we have this limit of 114.4, while we expect a limit a bit higher, and this, you know very well, led to many discussions in 20,000 to keep the LEP running or to kill the LEP. Unfortunately, the LEP was killed at that time. But the legacy measurement of this value was very important at the beginning of the LHC, because we know that where to look for the particle. Of course, another important and very important result comes from the Tevatron. The Tevatron was running for many years, and for some years this decade. And, you know, it's a PP bar collider. It's the place where the top quark was discovered, and it contributes a lot to the high energy physics at that time. And at the time of the discovery, at the time of 2011, 2012, they had already a lot of luminosity. In any case, this is the final result. This is not the luminosity that they had at that time. But in any case, they were able to exclude the Higgs clearly in the region of the Higgs decaying mainly into W's around 160 GeV. And they have, some evidence, more or less strong, of the presence of some particle around 125 GB. So, going to the LHC, you know the LHC is clearly a discovery machine. So this is the main goal of the LHC, and the LHC was built as a discovery machine. And of course, this machine has some challenges. There are a lot of not so interesting processes. So we have very large cross-sections. We have cross-sections of processes in which, okay, we are interested, but not so. And of course, the discovery processes have low cross-section. Apart from that, the backgrounds are very large. We have the PyLab, you know, this way in which the LHC is working with a lot of PyLab. This characterizes the working of the detector, the design of the detectors, the design of the upgraded detectors, and all that. Well, this is a summary of comparison, maybe something that Maricruz showed yesterday in another way. But you can see here that the interesting processes, the Higgs-related processes, have to compete with backgrounds that are factors of the order of 10 to the 8. So it's clear that to discover the Higgs and to measure the properties, we need to deal with this huge background. Of course, in an E plus E minus machine, you don't have these kind of problems. Well, talking about the LHC has performed, as I said at the beginning, extremely well. I would say that it's a machine that it's incredible. The LHC provides to the experiment this amount of data. If you compare with the data provided, the data that at the time of the Tevatron, they had of the order of 10 inverse femtobarn at the end of the experiment. We are going this 16 times that luminosity, and already at the end of the run one, we already have 3 times the luminosity at the Tevatron. The experiments have performed very well. You saw this morning that even in the run 3 they started with very large efficiencies. And this here you can see, which is the PyLab, the effect of the PyLab, measuring the mean number of interactions per crossing, and how the luminosity was recorded. This line shows you which was the design value at the LHC, and you see that more than 3/4 of the data has been taken in harsher conditions than expected at the beginning of the LHC. Well, this is a way in which I can show you how the detectors are performing, and these numbers are for the run 3. This is basically the identification efficiency for muons with this mass of the dimuons greater than 120 GeV. Sorry, you can see that these blue numbers corresponding to the run 1, and in run 2 we were able to improve the results of the run 1, even if the PyLab was much higher. And here you have an example from Atlas of the very incredibly good jet resolution that they have been able to obtain in these conditions. Well, from the discovery to the measurement, this has been a long way, and we started with this luminosity that was what we used to discover the particle. At the end of the run 1, many of the final states were established. Some of the production modes were established, and at the end of or using the data taken at the end of 2016, we were able to establish the Tau mode, the TTH production mode. with most of the luminosity of the run 2, or half of the luminosity of the run 2, we were able to establish this production mode, this decay mode that still is, I would say, it's very complicated, the BB bar. And of course, at the end of the run 2, we are able to start to see this kind of final states that are clearly not so easy, some properties and all that. Well, this is a reminder of which are the production modes of the Higgs. Here you can see, well, the gluon fusion is the one that provides well, the bulk of the data, and there are some of the TTH, as you see, is almost 100 times lower cross-section than gluon fusion, but in any case, here you have a coupling, and you have a coupling that it's very important to measure. And well, this is just well, kind of Feynman diagram that gives you an idea of the different theory parts that you have to take into account, and that at the end you are measuring the decay and you are measuring the production at the same time, so you are not able to measure separately these things. Another important thing is how the Higgs boson decays. And the Higgs boson decays, fortunately, in many ways. Imagine that the Higgs had the mass, let's say, 50 GeV heavier, like in this region. Most probably, we would have been only able to measure this couple of modes, and the rest would have been probably impossible, and many of the fermions would have been impossible to measure because the branching ratio to them was almost negligible. And of course, if it had been at the reach of the LEP, we probably missed the WW and the Z final state. So this value signals a region in which the cross-sections are large. They allow to look for fermionic decays, BB bar and tau tau and others, mu mu, and where the width of the Higgs is difficult. Very small. So, well, general comments on how we make the searches, the measurements, and all that. Well, typically, this is something that we typically did. We make blind analysis, so that means that we look typically to the background, to the Monte Carlo, and all that. And well, typically, what we give are model-dependent, so standard model-dependent results. And well, in any case, as you have seen before, we have a lot of final states with different sensitivities, with different properties, and this is what led to the experiments to study all the decay modes, all the production modes, because they have complementary sensitivities, and if we have to understand the properties of the particle, we need to study everything. So this, well, I now will show you some of the results obtained in the search and for the Higgs, the discovery, and the measurement. This probably is the first paper on the Higgs is about the measurement of the WW and the search for the Higgs to WW. You can see here that we were able to do something with this 36 inverse picobarn, that if you compare with the actual luminosity is almost nothing. But in any case, well, we were able to do things, and well, you can see here that even with this luminosity, we started to apply some artificial intelligence, machine learning techniques, and so on. So we, since the beginning, are trying to understand the backgrounds, are trying to squeeze all the phase spaces. We are trying to use the latest possible techniques and all that. Of course, you see here many results in which we try to understand the WW background, because this is the first final state, and finally at the end of the run 1, you can see that we were able to relate it with the Higgs search to make measurements of anomalous couplings of the main background to the Higgs. Well, the Higgs WW was a key contribution from many of the Spanish groups to the discovery. This final state is characterized because the spin correlations impose that the leptons, the electron and the electron and the positron, tends to go in a very small angle, so tends to go more or less in the same direction. And this is the way in which we are able to distinguish this final state from the main background, that is the WW. So we contribute with this final state, we contribute to the discovery. Here you see the plot that appears in the discovery paper, and we continue a lot with this channel. Atlas, the IFIC group has performed the analysis since the beginning until the observation of this final state using the full rank 1 luminosity. This also has been used to try to determine the spin parity of this particle. And well, at the end of the run 2, this year, we have presented in CMS the final results, the legacy results that not only shows the presence of the particle, but in this interpretation is able to target to different production modes and to different beams in the kinematics of the particle. So we have contributed a lot to the Higgs WW. Another important contribution was the Higgs to tau tau. The Higgs to tau tau is the first possible decay that can be observed of the Higgs to fermions. Fermions, of course, of the third generation, and the group of IFIC has contributed since the beginning, basically to the observation. And well, it's important to say that this final state also contributed to the discovery, apart from the gamma-gamma, Z-Z, and WW that were the traditional channels that were used in the combination. Well, using all this information, we were able also to establish very clearly that the Higgs has the quantum numbers that we expect, and we excluded the rest at 99% confidence level with this thing. So we make also contributions to the end of the rank 1 results, to this measurement in which well, not only you see the dependence on the couplings to the particle mass, but you start to see the first observation of the Yukawa coupling to the tau and establish the BBF production. Well, another important contribution of the Spanish community is TTH. TTH is something that established clearly the Yukawa coupling of the Higgs to the top quark. And well, the way in which we look for this final state is depends on the way of which Higgs decays to different particles. So traditionally, there were the multi-lepton final states in which the Higgs goes to WW, Z or taus, or the gamma-gamma or the BB final state. The IFI and the IFI groups contributed to this paper. This was the paper in Atlas giving the observation of this final state, and the same is true as I told you about the Higgs WW, with the contributions of the groups to the study of these kind of things. So, for instance, this is an intermediate result on TTH from IFI, contribution from IFI, and they are now studying the full luminosity of this to try to give the final result of this complicated channel, because TTH and TTW has basically the same final state. We have fakes, the control of the backgrounds is not so easy, and so on. So we did the same in CMS, so various groups in CMS contributed to the observation of the TTH, and we have continued we have provided the final result using all the luminosity of the run-2, making a lot of different things, multi-classification, using deep neural networks and all that, to try to get the sensitivity that we were able to reach, that is this 5 sigma sensitivity for to establish the TTH production in the multi-lepton final state, and we are able also to measure these kappas that are the ratio between the couplings and the couplings of the standard model to the corresponding particle. We, as Lourdes presented on Wednesday, we have also studied the CP interpretation, and we studied the WW set final state, the multi-leptons, but when combining with the rest of the channels, we are squeezing the possibility of these values to be beyond the standard model. Well, the phi also contribute to this very, very difficult channel, that is the TTH when the H goes to BB bar. So you see here the result. This is a clear example of something that has to be studied using the run-3. You see the mu value is relatively small, and this is something is compatible with the standard model, but it's relatively small and well. Well, with that, we have tried to compile all the information that we obtained in the run-2 in these 2 papers that appear at the time of the celebration of the discovery. And well, here you have a way in which you present the different production modes as a function of the sigma times the branching fraction normalized to the standard model prediction. You see that within errors there are channels that are well established, others not so well. And here you see clearly that this particle couples to the particle mass. Let me say one word here. This is the mu. This is the mu. This corresponds to the global fit. This is Atlas, I believe. And well, you can see here that we have a lot of work to do. We have the final precision is at the level of 6%, but you can see here that the statistical, the experimental, the theory, and the understanding of the background in the theory are basically at the same level. So that means that for the run-3, we need to continue taking data. We need to understand our experiments. We need the theory community to try to get to decrease these numbers up to the level of below 1%. So everything is here. Well, I have a couple of minutes. This is another way of presenting what we have learned in these years. I believe that everyone is convinced that we have seen the set. We have seen, the gamma. I believe we have seen the WW very clearly, and we start the tau, and we start to look for difficult channels, very low branching fraction channels and all that. Well, let me go in this last minute to the thing that is probably what will be the thing that we'll study during the run-3 and the high lumi, that is the di-Higgs production. This di-Higgs, as you can see here, has basically 1,000 times lower cross-section times branching fraction than the Higgs, and we have to study this kind of processes combined with the possibility of having beyond standard model physics. The results that we have is, the CMAT group is studied this BB tau channel. One of the Higgs goes always to BB bar because the branching ratio is the highest. And, then we choose the tau, the gamma in the case of the FIG group because they have either a low background or very good mass resolution. Well, you can see that I think Aurelio showed already this morning that we are close, well, relatively close to the standard model. We are at the level of 3-4 times the standard model, and we are improving. So it's probably true that we will be able to establish this particle, this decay mode at the end of hopefully the run 3 or the beginning of the high luminosity. So let me Begoña, say one thing. I have here another topic that has been continuation of the efforts to the measurement of the properties that are the search for additional things. So let me go very fast. We have been looking for heavy Higgses, for particles that couples to the Higgs and other particles, to the beyond the standard model going to tau, to charged Higgs, to lepton flavor violation Higgs decays that can give us some light on the anomalies in LHCb and all that. But not only that, also to dark matter. This is an extension of the Higgs to WW that has been done at IFCA. Also, this connection with the dark Higgs and all that. And well, this is my last slide. What is our intention for the run 3? Our intention for the run 3 is to continue studying and to measure the processes in which we have been involved in the run 2, the Higgs WW, TTH, the Higgses, make this kind of measurements and look to these alternative scenarios. And well, I believe that you know this let's say, possibility of improving these values that were obtained during the European strategy. That basically tell us that at the end of the run of the high Lumi, we can have something close to 5 sigma, but as has been said many times here, all we believe that we will be doing better than that and better than that. Well, and finally, of course, we have, this has been an enormous effort by the community. We have made a lot of contributions to the study of the properties of the Higgs, and well, I believe that our community is in an excellent position to fully exploit the run 3, the high Lumi, with the upgraded detectors. This is one of the tasks that is consuming a lot of time to us. And of course, the precision measurement of the Higgs are still very important, and as I said before, probably at the beginning, probably will drive the future of high-energy physics. Thank you very much. I'm sorry.
Thank you, Javier. So thank you for this very complete review, starting from the historic past and to the prospects in the future. So 1, 2 questions? Quick questions?
Hi. Concerning precision, there is always a challenge between theories and experimentalists about precision, but say there are many very precise calculations making from the theory from the theory side. Say from the theory side, we can arrive to 3 loops in many perturbative acoustic calculations. We can use effective field theory with precision of about 1 per mil or less than 1%, something like this. Can we imagine that we arrive at such a precision with HL or RAN3, and in which observable?
Well, as you can imagine, one thing are the calculations, and what we need.
I know.
What we need are the Monte Carlos. So I believe that this is well. Our aim is to reach the 1% level of, as I told you before, in statistics, in understanding of the detector, systematics, theory contributions. In Monte Carlo, and so on. Of course, we will compare with effective field theory calculations, with all that, but I don't believe that without a Monte Carlo at the NNLO for the signal and for the backgrounds, we can reach this kind of sensitivities. So 1% is fine, I would say. Sven.
Yes.
I'm afraid we are not in such a good state from the theory side. I tried to make the point yesterday that theory can even be the limiting factor in some of these measurements. So we can do many calculations, but they are very, very complicated, and there's still a long way to go to get to the precision where, for example, the high luminosity LHC will get us, hopefully, from the experimental side, or going even further. Yeah? So I don't think we are there, by far not.
Okay, so I think theoreticians also have to work. Thank you, Sven, for the message. And I think if there is no urgent question, we continue because we are already late. And now we are changing. So I think we first thank Javier again and all the speakers in the all the speakers in this session. So now we are changing the spirit and still continuing with the Higgs and the LHC. There will be some contribution, and we are going to bring some tribute to the pioneers and the researchers who first led and put in place the experiments for the LHC. And for that, I think it's Nuria who is going to come now. Ah, ¿es Nuria? No, it's you? Ah. Sí, she's supposedly... ¿Podéis buscarle alguno, por favor? Okay.
Yeah, maybe in the meantime, we should actually also thank Nuria and Jesus Puerta from CIEMAT and Maricruz, who contributed to this, the making of this video. And while Nuria is coming.
Nuria is coming.
Yeah, so as Begoña already said, I mean, the contribution from Spain in the discovery of the Higgs boson has become very evident from Javier's talk. But the Spanish contribution goes beyond that. We participate in many physics analysis and in key aspects of the operation. And this, of course, it's thanks to the contribution of many people throughout the years, but especially thanks to those pioneers who promoted the participation of Spain at the LHC. So with this video, we wanted to acknowledge that.
Tú dale.
Sí.
Es un vídeo de unos minutitos.
¿Ya lo pongo? ¿El volumen? ¿Hay alguien ahí dentro? Sí. Pues que ponga el volumen como hizo ayer. No está puesto aún. Es que le tienen que activar el volumen desde ahí. ¿El volumen del vídeo?
A ver si lo arreglamos o no se puede, ¿vale?
¿El qué, perdón?
A ver si se puede arreglar o no. Si no se puede, pues pon una excusa. Sí debería estar funcionando. Ya, pero te pueden pasar muchas cosas.
Hay micro y así digo una cosa. Sí. Vale, toma. Voy a decir ya algo así. ¿Este va? Vale. Después vamos a cerrar el Paraninfo cuando nos vayamos a comer y no se abrirá hasta las 4 menos cuarto para coger las maletas y irnos a los buses. Entonces, si alguien quiere coger la maleta antes de las 4 menos cuarto, que se la lleve con él a comer. ¿Vale? ¿Y era algo más? María José, ¿algo más? Lo de las maletas y ya está. Y los autobuses nos recogerán en el sitio de siempre, de donde nos dejan siempre y nos recogen, para ir al aeropuerto, uno al aeropuerto y otro a Bilbao. Ayer en el descanso lo probamos y funcionaba. Sí, pero ayer lo probamos. Ayer lo probamos y funcionaba. Y hoy estaba probando lo de la entrega de premios. A ver si... ¿Cambiarlo? No sé. ¿Lo pongo? Este año celebramos el 10º aniversario del descubrimiento del bosón de Higgs. Lo puse desde mi pen. ¿Tiene eso algo que ver?
Pon otra vez.
Uno de los grandes logros de la... Ya funciona. Este año celebramos el 10º aniversario del descubrimiento del bosón de Higgs, uno de los grandes logros de la comunidad científica que participa en los experimentos del Gran Colisionador de Hadrones del CERN. La participación de España en el descubrimiento del Higgs y en otros brillantes resultados del LHC no hubiera sido posible sin la ambición y valentía de aquellos que iniciaron esta aventura con fuerza y determinación. A todos estos pioneros queremos recordar hoy, agradeciéndoles su iniciativa, pero sobre todo su gigantesco esfuerzo.
El grupo de IFAE en Atlas se creó en 1993. Mi iniciativa fue poner el grupo a trabajar en el calorímetro hadrónico. Así que, tras unos experimentitos que tuvieron mucho éxito y un tiempo en el test beam, el grupo cogió la responsabilidad de construir más o menos la cuarta parte del aparato, un gran cilindro de 600 toneladas de una altura de más o menos 8 metros, que se desarrolló en parte en IFAE y que se acabó en el año 2002.
Una vez encarrilado el desarrollo de Talcal, IFAE en el año 2000 empezó una nueva actividad, el desarrollo de software para la granja de ordenadores del trigger, el event filter. Con la ampliación del grupo se transformó también en un trabajo de operación del trigger y desarrollo de algoritmos cada vez más complejos. En 2008, con otra ampliación del grupo, IFAE ha empezado el desarrollo de detectores de silicio de píxel tipo 3D en colaboración con el CNM. Se instalaron en el IBL y en AFP, y está la preparación para Phase 2 está en marcha. A lo largo de todos estos años, IFAE ha desarrollado un programa de física muy amplio, liderando muchos análisis importantes, y hemos también asumido posiciones de management dentro de Atlas que han sido relevantes.
Para participar en Atlas, desde el caso de Valencia, gracias a colaboraciones bien establecidas, por ejemplo, Valencia con Barcelona, en un proyecto muy interesante como es el de TICAL, que es el detector del calorímetro hadrónico, y el detector de trazas, en el cual también participó Valencia.
El proyecto para España en 1996 era tecnológicamente muy ambicioso. Pero la ilusión y compromiso de los equipos del IFIC de Valencia y del CNM de Barcelona hicieron posible lo que parecía imposible.
Bueno, la historia del detector de trazas de silicio de Atlas comenzó aquí, en esta sala blanca, en el año 2003, con un gran equipo de personal, y los que nos faltaba en ese momento de experiencia pues lo pudimos suplir con mucha motivación y mucha dedicación.
La computación grid de Atlas fue una actividad que empezamos en 1999. Una de sus características es que no para nunca, o sea, siempre está en funcionamiento.
En 1995, Fernando Barreiro, como director, pensó que con la gran experiencia que tenía el grupo en calorimetría se podría contribuir al calorímetro electromagnético de Atlas, y se puso en contacto con el director del proyecto, Daniel Fournier. Por aquel entonces estaban realizando pruebas con un prototipo de calorímetro de muestreo con forma de acordeón, donde el material absorbente era plomo y el material sensible argón líquido. Estas pruebas con haces de partículas se realizaban dentro de la colaboración RD3 en el CERN. Fernando Barreiro envió al CERN a dos miembros del grupo, Luis Hervás y José del Peso, para participar en RD3. Poco después fue Daniel Fournier quien propuso al grupo de la UAM la tarea de construir el calorímetro electromagnético de la zona ENCAP, en colaboración con el CPPM de Marsella. Además de los mencionados, fueron iniciadores de la construcción Luis Lavarga y los ingenieros Francisco Gallardo y Pablo Romero.
En 1996, Juan Fuster del IFIC vino al CNM a proponernos colaborar en detectores de partículas para el CERN, que se harían en nuestra sala blanca. Al principio no entendimos de qué nos hablaba, pero nos gustó la idea y nos atrapó. De esta forma comenzamos una nueva línea, siendo yo el responsable. Acababa de nacer el grupo de detectores de radiación del CNM.
En 1999 yo me fui de estancia postdoctoral a California a trabajar en el daño por radiación de la electrónica de lectura del SCT. Así entrábamos en un nuevo tema que era los efectos de la radiación. Ya en 2002 comenzó en nuestra sala blanca la primera producción para el CERN. Se trataba de los pitch adapters o fan-ins. En 2 años y medio fabricamos unas 2.700 piezas que aún están en funcionamiento en el SCT de Atlas.
La primera fabricación de los detectores empezó unos años más tarde. Nuestros sensores llevan funcionando en el experimento Atlas de CERN desde hace más de 10 años. El grupo de detectores de radiación ha crecido y ahora somos más de 20 personas.
La participación del CIMAT en el LHC se remonta a principios de los años 90, donde ya estábamos trabajando en varios proyectos de I+D del CERN. Se participó en la preparación de las expresiones de interés de dos propuestas, CMS y L3P, que se presentaron en el simposio de IBIAN en 1992. Se estaban siguiendo dos líneas de I+D. Por una parte, el desarrollo de calorímetros a pequeño ángulo y por otra, el diseño de cámaras de muones de tecnología similar a las construidas por CIEMAT para el experimento L3. Fue en 1995 cuando CIEMAT decide finalmente que su contribución a CMS serían las cámaras de deriva DTS para el detector de muones y su sistema de alineamiento. CIEMAT además se responsabilizó de la contribución in-kind de nuestro país al Fondo Común de CMS, financiando la construcción de grúas por parte de una empresa española que están equipando el punto 5 del LHC. Y bueno, finalmente recordar que CIEMAT junto con IFAE crea y opera desde sus comienzos el PIC.
En Madrid se fabricó la primera cámara de T completa, validando así el proceso de fabricación para todas las sedes de producción. Entre 2000 y 2006, el CIEMAT produjo 70 de las 250 cámaras de test, así como toda la electrónica de readout y buena parte de la mecánica y de la electrónica del sistema de alineamiento. En 2001 se inicia una estrecha colaboración entre el CIEMAT y la Universidad Autónoma de Madrid, Fue responsabilidad de la Universidad Autónoma de Madrid diseñar, construir y operar el Drift Tube Track Finder, un sistema novedoso de reconstrucción de trazas para el trigger de muones de nivel 1. Han sido muchos los logros de este equipo CIEMAT-UAM a lo largo de los años, tanto en la instalación, la calibración, la puesta a punto y la operación de CMS, así como el procesado de los datos, al análisis de física y producción de resultados. Logros que han sido fruto de un gran esfuerzo colectivo.
Bueno, el grupo tenía ya bastante experiencia en colaboraciones internacionales y además acababa de llegar al grupo Teresa Rodrigo, entonces iniciamos conversaciones, pues en particular con un grupo de Padua y demás, para participar en el futuro del LHC.
Y hemos trabajado desde entonces mucho en el sistema de alineamiento de muones, que es el trabajo principal que tenía el IFCA junto con el CIEMAT.
Partiendo de un grupo muy pequeño, inicialmente liderado por Teresa, pues bueno, pues fuimos ya aumentando nuestra participación, pero vamos, siempre con la figura de Teresa como la persona que nos iba liderando.
Yo entré ya un poquito después de que el grupo se uniera a CMS, entré en el 2002 y la verdad es que bueno, pues la cabeza de impulso que yo vi en ese momento era Teresa Rodrigo, por supuesto.
Hizo que nos metiéramos en CMS, la que tiró de los primeros proyectos, siempre apoyó a todo el mundo a que aprendiera cosas nuevas y se metiera en proyectos nuevos. Creó bastante grupo, ella trataba de que todos fuéramos un grupo y fuéramos a una.
El Grupo de Física de Altas Energías de la Universidad de Oviedo comenzó a trabajar en el acelerador en el EHC desde sus comienzos, como continuación de nuestra participación en los aceleradores previos en LEP y en el Tevatron en la década de 2000 a 2010, y justo en 2010 comenzamos a trabajar en el análisis de datos de los datos del LHC con el objetivo de encontrar el bosón de Higgs.
En estos 10 años el grupo ha crecido sustancialmente, incorporándose al Instituto de Ciencias y Tecnologías Espaciales de Asturias, con la incorporación de nuevos estudiantes, estudiantes de posgrado magníficos. En 2012 tuvimos la suerte de que a Higgs, Angler, al CERN le dieron el Premio Príncipe de Asturias de Investigación Científica y Técnica unos meses antes de saber que ya tenían el Premio Nobel, con lo cual contamos con ellos aquí, con Rob Joya, con Roberto Bertolucci, director general y director científico del CERN, lo cual fue una experiencia, además de toda la comunidad española de física de partículas, lo cual fue una experiencia magnífica que yo recuerdo con mucho cariño, con todos ellos en la Facultad de Ciencias, con todos los estudiantes emocionados, mirando por las ventanas, tratando de encontrar un segundo para estar con los entonces Premios Príncipe de Asturias y futuros Premios Nobel.
Hola, soy Abraham Gallas, el coordinador del Instituto Gallego de Física de Altas Energías en el experimento del XIV del CERN. Nuestra institución ha sido una de las fundadoras de este experimento, en el año 1995. Los impulsores han sido el profesor Bernardo Areva, el profesor Máximo Pló, la profesora Ángeles López e incluso yo mismo, que en aquellos años empezaba haciendo mi tesis doctoral. Los hitos importantes de nuestra institución en el experimento han sido la construcción del Silicon Tracker y la construcción aquí en Santiago de un centro Grid Tier 2. En estos momentos, nuestros hitos importantes conseguidos es la construcción del BEL, del Vertex Locator, que ha sido instalado y en estos momentos lo estamos comisionando en el experimento. Esperamos recoger muchos datos el año que viene para realizar física.
L'Institut de Ciències del Cosmos de la Universitat de Barcelona comença a participar en l'experiment LHCb des dels seus inicis l'any 2009, amb Lluís Garrido com a investigador principal del projecte i amb l'objectiu d'estudiar les diferències entre la matèria i l'antimatèria.
Primer, l'HCb el que vol és aportar llum en aquestes diferències que encara no es coneixen o es coneixen poc.
A l'XIV tot just hem començat a prendre dades i ja estem treballant en un nou projecte. Es tracta d'una nova versió de l'experiment que començarà a funcionar d'aquí uns quants anys quan el ritme de producció de col·lisions de l'LHC sigui molt més gran.
El detector que portem des de Barcelona està situat aproximadament aquí
a uns 12 metres d'on es produeixen les col·lisions. El nom del detector és SPD, que són les sigles en anglès de detector de cel·les centellejadores.
En el nostre equip d'enginyers vam dissenyar l'electrònica que processa la senyal de l'SPD. Com ja he comentat, aquesta electrònica ha de funcionar a un ritme vertiginós i a més no pot fallar mai.
A dia d'avui, l'ICUB segueix investigant els efectes de la violació de la simetria CP i participant en els dissenys d'electrònica de fotosensors amb un equip de 21 investigadors liderats per Eugeni Graugés.
Dada la trayectoria en física de sabor, y en particular en las factorías de BES, decidimos entrar en 2013 en un experimento tan relevante como el XIV, de la mano de la Universidad de Barcelona. Ahora somos un grupo consolidado e independiente de más de 10 investigadores, con una considerable repercusión tanto en la física como en el detector.
En el año 2000, los estudios coordinados por el CERN indicaban que la cantidad de datos producidos por los experimentos del LHC como Atlas serían mucho mayores y que además los datos serían mucho más complejos. Entonces, la única manera de enfrentarse a esto era interconectar con fibras ópticas centros en los diferentes países participantes y que estos centros instalaran sistemas con almacenamiento masivo fuertemente conectado a miles de ordenadores. Nosotros ya teníamos experiencia de la anterior generación de experimentos en el acelerador LEP, el experimento Aleph, en montar este tipo de sistemas. Por tanto, el IFAE y el CIEMAT unieron esfuerzos para crear el PIC y contribuir así un centro de estas características al sistema mundial del LHC.
Los años han pasado y todo el esfuerzo de aquellos que decidieron comenzar esta aventura ha merecido la pena. Actualmente la contribución de los grupos españoles en los experimentos del LHC es muy significativa y bien reconocida a nivel internacional. Vaya con este vídeo nuestro pequeño homenaje a los que empezaron este camino, ese que aún hoy en día seguimos recorriendo juntos.
Vale, pues un aplauso desde luego a todos los que han colaborado en la realización de este vídeo y bueno, pues a todos los pioneros que han ido saliendo. Realmente es o ha sido y sigue siendo un proyecto vital para la mayoría o muchos de nosotros y muchos de los que por supuesto estaban en el vídeo, ¿no? Un proyecto al que ha llevado buena parte de su vida profesional. Bueno, ahora me he ido al español porque creo que lo que viene ahora es la entrega de premios de divulgación, lo va a llevar Nuria. ¿Es el PPT? Perdona, Nuria. Bueno, pues tenemos la 9ª edición del concurso de divulgación científica del CPAN y Rocío y Nuria van a llevar la entrega de ello mismo.
¿Funciona? Sí, ¿no? Vale. Pues vamos a comenzar el acto de entrega de premios de esta 9ª edición del concurso de divulgación científica que organiza el Centro Nacional de Física de Partículas, Astropartículas y Nuclear en colaboración con el Centro de Ciencias Pedro Pascual de Benasque. Este año va a entregar los premios a los ganadores Rocío Vilar Cortavitarte, investigadora del Instituto de Física de Cantabria y profesora del Departamento de Física Moderna de la Universidad de Cantabria. Hoy queremos, además de su excelente trayectoria investigadora, queremos también hoy recordar y homenajear un poco su trabajo todos estos años en la Red Europea de Comunicación en Física de Partículas y en la que me releva este año. Así que nada, muchas gracias por ofrecerte a entregar los premios, es todo un honor. Vale, vamos a empezar. Este año tenemos las 5 categorías de la entrega del concurso tradicionales, artículos de divulgación, webs, blogs, vídeos, experimentos, demostraciones, aplicaciones, trabajos publicados en medios de comunicación y con motivo del 10º aniversario del descubrimiento del bosón de Higgs hemos añadido una modalidad nueva que es la de trabajos de formato libre con temática el bosón de Higgs. Hemos recibido 39 candidaturas en total, 11 artículos, 6 candidaturas para webs o blogs, 11 vídeos, 2 experimentos, demostraciones, 4 trabajos publicados en medios de comunicación y 5 trabajos de temática el bosón de Higgs. El jurado de esta 9ª edición ha estado compuesto por 4 personas de las áreas que representan cada una de ellas una área del CPAN, una persona externa y la secretaria del jurado, que soy yo, que no tengo voto, pero bueno, ahí he estado. Clara Cuesta del CIEMAT representando el área de Física Experimental y de Partículas como presidenta del jurado, Bruno Zamorano García representando el área de Física de Astropartículas de la Universidad de Granada, Óscar Moreno Díaz representando el área de Física Nuclear de la Universidad Complutense de Madrid, Valentina de Romeri del Instituto de Física Corpuscular representando el área de Física Teórica, como miembro externo al CPAN, Francisco Villatoro Machuca, profesor de la Universidad de Málaga y divulgador científico con su blog La ciencia de la mula Francis. Así que vamos a empezar ya con la entrega de premios. La primera modalidad es el artículo de divulgación y la premiada es Ángela Bernardo Álvarez por su artículo Protonterapia, el rayo que no quema. Ángela es una chica que ha hecho muchas cosas, tiene un doctorado en Derecho, pero ella es biotecnóloga, si no me equivoco, y actualmente es redactora en la Fundación Cibio, y el jurado ha valorado de su artículo la originalidad, lo bien escrito que está, el estilo del texto y sobre todo cómo combina arte con física. En el artículo se expone la protonterapia, las características más importantes y su diferencia con otros métodos de radiación más tradicional. Sube a recoger el título su madre Carmen, ella no ha podido venir, así que nada, Carmen. Lo que sí es que nos ha mandado un vídeo, a ver si podemos verlo.
Buenos días, soy Ángela Bernardo y en primer lugar quiero agradecer al CPAN la organización de estos premios de divulgación científica. Durante la última década han reconocido sin duda el trabajo especializado en el ámbito del periodismo, de la comunicación y de la divulgación de la ciencia y para mí es un honor estar en la lista de trabajos premiados, en este caso por un artículo de divulgación que escribí centrado en el ámbito de la protonterapia, es decir, de una de las aplicaciones prácticas de la física en el ámbito de la salud y en particular en el tratamiento del cáncer. Muchísimas gracias al jurado por haber reconocido este trabajo, la verdad es que me siento muy honrada y muy feliz de poder figurar entre las personas premiadas con este galardón. En segundo lugar, me gustaría disculparme por no poder estar esta mañana en Bilbao para recoger el premio del CPAN. Me encuentro en Madrid, dado que hoy también es el Día Internacional contra la Violencia de Género, 25 de noviembre, y hace algún tiempo me comprometí a participar en una mesa redonda en la Universidad Autónoma de Madrid por la publicación del libro que realicé el año pasado, Acoso, Me Too en la ciencia española, y por este motivo no puedo estar hoy en Bilbao. Y por último, quiero dedicarle el premio a mi familia por su apoyo y su cariño constante, por su estímulo. La verdad es que este trabajo se lo quiero dedicar especialmente a mis padres, que se encuentran hoy en Bilbao, por acompañarme siempre y bueno, pues animarme a dedicarme a esta profesión tan bonita. Muchísimas gracias.
Continuamos ahora con el...
Buenos días.
Ay, ¿por qué se vuelve a poner? Ahora. con el premio de la modalidad Webs Blogs, que el jurado ha decidido otorgárselo a José Adrián Castelo Martínez por su blog Física Tabú, un blog donde él divulga muchísimas áreas de la física, sobre todo las áreas temáticas del CPAN. Y el jurado también ha valorado mucho los toques de humor que tiene el blog y la forma tan atractiva en la que comunica la ciencia y explica los temas más complejos de la física. Así que, por favor, Adrián, baja a recoger el premio, que él sí que sé que está por aquí. Ahí está. Adrián es graduado en física y actualmente trabaja como profesor de secundaria y bachillerato en un instituto de Albacete. Y en sus ratos libres divulga en su blog de física.
Nada, seré muy breve realmente. Pues agradecer mucho al CPAN por la organización de este concurso y simplemente pues algo que quería decir es que cuando hace 10 años empecé a interesarme mucho por la física, entrando ya a la carrera, veía el logo del CPAN en los blogs de divulgación más famosetes como Cuentos Cuánticos o como el de Francis, y luego lo vi también que lo ganó Javier Santaolalla, lo ganó el IFT, y o sea que ahora ganarlo yo me parece muy... Vamos, que me emociona y me parece algo grande. Así que muchas gracias.
La siguiente modalidad es la modalidad de vídeos. El vídeo del telescopio més gran del món de Toni Bertólez Martínez ha sido el ganador de esta categoría. Es un vídeo muy guay, muy divertido, muy dinámico, en el que él explica un poco cómo funciona IceCube, el telescopio de neutrinos, y el jurado sobre todo ha valorado su capacidad de comunicación y lo dinámico que resulta el vídeo, la calidad audiovisual que tiene. No sé si vamos a poder ponerlo, porque se me ha olvidado. A ver. Ah, sí, ahora sí que va. No va. Lo pongo al final de la entrega. Y nada, es un vídeo súper chulo que me ha dicho que esta tarde lo va a colgar ya en YouTube, ahora está en oculto. Así que nada, os animo a todos a verlo. Y bueno, Toni, sube a recoger el premio antes de que me pase otra cosa.
Bueno, qué vergüenzas, me están temblando un poco las piernas. Y suerte que no me he puesto el vídeo, porque si no estaría aún con mucha más vergüenza. Ay, qué miedo. Bueno, muchas gracias al CPAN, es un honor, es un privilegio haber estado valorado con este premio. Me sabe mal porque he llegado hoy y yo soy aquí investigador también en neutrinos y no os he podido conocer a la mayoría, pero bueno, espero hacerlo en el futuro. Y nada, solo aprovechar que bueno, también hoy es 25 de noviembre y ya que estamos también premiando la comunicación y la divulgación de la ciencia y de los neutrinos, por ejemplo, que son súper interesantes, también divulgar y comunicar los sesgos de la ciencia, por ejemplo, pues, a través de visibilizar esta violencia, no solo física, que hay también pues, para con las mujeres. Muchas gracias.
Toni es estudiante de segundo grado de doctorado y durante tanto como el grado como en estudios de posgrado ha estado muy involucrado en actividades de divulgación. Así que se nota que tiene experiencia. Y luego el jurado también ha decidido conceder una mención a XIV en esta modalidad al vídeo "Este es el líquido más perfecto del universo", realizado por el XIV en colaboración con el youtuber Quantum Fracture. El siguiente premio corresponde a la modalidad Trabajos publicados en medios de comunicación y va para Jesús Méndez González por su artículo "Así consiguió el insondable bosón de Higgs reventar los medios", que lo ha publicado en la agencia Sync. Es un artículo que trata sobre el fenómeno sociológico que tuvo y la repercusión que tuvo el descubrimiento del bosón de Higgs en los medios de comunicación. y además está escrito de una forma que atrapa, la lectura es muy dinámica y muy original. Y el enfoque, ya os digo, es un enfoque sociológico muy interesante. Así que nada, Jesús, sube a recoger el premio, no sé por dónde. Ah, está ahí. Jesús actualmente es escritor científico y colabora con muchas empresas de comunicación científica y grandes periódicos.
Hola. Muchas gracias a CPAN, obviamente al jurado por haber elegido el artículo. Gracias también a Pampa García Molina, que fue la que me propuso la idea de hacer este reportaje, cuando todavía era jefe en la agencia SYNC. Un reportaje que además me gustó mucho escribir porque permitía 10 años después del bosón pues explicar un poco de qué iba, obviamente de una forma muy general, pero sobre todo tratar de entender cómo fue que una partícula tan compleja, tan separada en teoría de la vida real, pudiera llegar a prácticamente las portadas y absolutamente todos los medios de comunicación de todo el mundo. Como seguramente a través de la figura del héroe individual, del poder de las metáforas, del hecho de que fuera una teoría que necesitó de una infraestructura internacional gigantesca para poder demostrarse, de las campañas de prensa o de las teorías conspirativas, pues logró todo eso y por encima, por debajo de todo ello, supongo que estaba la curiosidad por entender qué tenemos. Nada más. Muchas gracias.
En esta modalidad, el jurado también ha decidido conceder una mención a XIV al artículo Bosón de Higgs, 10 años del descubrimiento del siglo hasta ahora, de Alberto Casas González, que es un artículo publicado en El País. Continuamos con el siguiente premio, que corresponde a la modalidad experimentos y demostraciones, y esta vez va para un grupo de personas: Ana Argudo, Rafael Vallabriga, David Corrons, Eugeni Grauchés, Yolanda Huguet, Esther Pallarés, Daniel Parcerisas, Herman Pino, Francesc Salvat y Sonia Tarancón, por su trabajo Detectores híbridos para visualizar partículas en educación secundaria. Ese trabajo muestra cómo aplicar unos detectores fabricados con tecnología del CERN en educación preuniversitaria para enseñar física experimental, sobre todo de partículas, en ámbito de educación secundaria y sobre todo de educación preuniversitaria. El proyecto está enmarcado este trabajo está enmarcado en el proyecto Admira, que es una propuesta de la sección de microelectrónica del CERN, del Instituto de Ciencias del Cosmos de la Universidad de Barcelona y del Colegio de la Sagrada Familia de Sabá. Ellos tienen una iniciativa de divulgación que se llama Admira y que utilizan este tipo de detectores para enseñar física de partículas en institutos y colegios. Así que recoge el premio Daniel Parcerisas, uno de los autores. Por favor, Daniel, baja. Ahí está. Miguel, con el móvil tuyo. Porque no va la cámara, creo. Estamos teniendo problemas con la cámara. Ya está. Bravo.
Gracias, Nuria, y al resto de la organización, porque sin vosotros no estaríamos hoy aquí. Además, me has ahorrado decir todos los nombres, que era una de las cosas que tenía en mi tarea, por lo tanto me puedo centrar un poco más en explicar pues, que este proyecto empezó hace 4 años, un poco por casualidad, de la colaboración entre el CERN, la Universidad de Barcelona y mi colegio, y que ahora pues tenemos 5 detectores, más de 25 colegios participando, y que la cosa pues ha ido creciendo y está funcionando muy bien, y que se pueden hacer cosas muy interesantes. Pues bueno, en principio gracias a todos estos desarrollos que habéis presentado de estos pioneros del CERN, que empezaron hace unos años y que han acabado produciendo pues tecnologías que resultan aplicables más allá de lo que sería la propia detección de partículas. Por otro lado, agradeceros el importe metálico del premio, porque ¿qué os voy a explicar yo sobre los problemas de financiación de la ciencia? Pues imaginaros en los colegios, que es todavía más complicado, y seguro que tener otro detector nos va a venir muy bien para poder llegar a más chicos. Y por último, pues agradecerle a mi mujer también el soporte y sobre todo las correcciones gramaticales y de estilo que le hizo al último borrador, ¿vale? Que yo creo que lo dejaron niquelado. Gracias.
Al jurado y a mí nos gustaría destacar que este trabajo además tiene adaptaciones, esta demostración tiene adaptaciones para alumnos con necesidades especiales, así que bueno, creo que es algo que merece valorar. Y por último, en la modalidad temática del bosón de Higgs, el premio va para un conocido, para Javier Santaolalla Camino, por su libro "¿Qué hace un bosón como tú en un Big Bang como este?", en el que narra el descubrimiento del bosón de Higgs, un poco también en primera persona y de una forma dinámica, enfocada hacia jóvenes y con su objetivo que sabéis que es pues, fomentar las vocaciones científicas y divulgar lo que él ha hecho y lo que hacen sus compañeros del campo. Así que sube a recoger el premio una de sus jefas, que él dice, Isabel Josa. Un aplauso. Javier no ha podido estar hoy aquí porque tenía una conferencia en Barcelona, pero bueno, se pasó el miércoles a saludar a todos y bueno, ya sabéis quién es, divulgador científico, trabajó en el CIEMAT, en CMS y como no ha podido estar aquí nos ha mandado un vídeo de agradecimiento.
¡Hola! Aquí Santaolalla realizando un pequeño viaje en el tiempo porque estoy en el presente, pero que es el pasado para aparecer en el futuro. Ya saben lo que quiero decir. Y bueno, aunque no he podido estar, nos hemos visto estos días, o supuestamente, porque esto es del pasado, así que no sé cómo van a ser estos días, pero supuestamente nos hemos visto en Bilbao. Para mí habrá sido, supongo, un gran placer verles a todos. Y no puedo estar en la ceremonia de entrega, pero aún así quería estar presente de alguna manera. Y por eso este vídeo, que para mí es muy importante. Voy a intentar condensar todo lo que quiero decir en muy poco tiempo, porque el tiempo es muy valioso. Y quiero condensar el agradecimiento absoluto y pleno por este premio. Yo sé que todo el mundo dice que todos los premios son especiales, pero este es realmente muy especial y tiene un motivo por el que sea especial. Este libro, el bosón, ya no sé cómo se llama, que hace un bosón como tú, un Big Bang como este, incluye esos 4 años maravillosos que compartí con muchos de ustedes. Sí, se imagino que por ahí estarán mis jefas. Hola, Isabel y Begoña. Puede que incluso Juan Alcaraz, hola también. Y luego un montón de compañeros que, pues no sé si estará por ahí María Cepeda, Rebeca, Pablo, bueno, todos que han formado parte de esta experiencia, de esta historia, y a todos les puedo estar muy agradecidos. Pero tengo un especial agradecimiento por este premio, porque yo trabajo en divulgación, en comunicación de la ciencia, me he ido al lado oscuro desde hace tiempo, pero creo que hago un trabajo, creo que muy bonito, que es el de transmitir la ciencia al público general, crear nuevas vocaciones, mostrar la importancia del trabajo científico, y tiene una importancia, yo creo que muy especial, de dar valor a las investigaciones, demostrar por qué la ciencia es importante en nuestro mundo y dar reconocimiento al trabajo del científico y la científica. Y de ese trabajo que yo creo que en lo que estoy aportando, y creo que es parte del sentido de todo lo que hago, que estoy muy pegado al público, estoy muy pegado a la gente, a la sociedad, que del otro lado, que es la investigación, lo valoren y lo reconozcan, no solo le da mucho sentido a mi trabajo, sino que me anima a seguir haciéndolo. Así que, pues muchas gracias por el reconocimiento, que venga de personas que son compañeros y que además, como digo, son los que están detrás de las grandes investigaciones de ciencia en física de partículas, altas energías nuclear en nuestro país, pues tiene valor doble, triple, mucho más. Así que, por no extenderme, muchas gracias. Es muy apreciado este premio y creo que va a ser por lo menos va a ser un gran empujón para mí, para mi carrera y para ese bonito trabajo que creo que estoy haciendo de promoción, popularización y nuevas vocaciones científicas. Pues tanto el bosón de aquí como yo estamos muy agradecidos y le mandamos un grandísimo abrazo a todo CPAN. Hasta pronto, chao.
Bueno, muchas gracias a todos por asistir al acto de entrega, sobre todo a los premiados que han venido desde distintas partes de España a recibir este premio y nada, nos vemos en próximas ediciones. Un saludo a todos.
El del chico. Bueno, ya un poco como despedida, cierre de la sesión, no sé si queréis, por supuesto, dar las gracias a los organizadores de esta edición y, bueno, Tony, creo que es el momento de que...
Bueno, creo que todos tenemos prisa por ir a comer, pero antes sí que quisiera agradecer a la organización local por habernos acogido aquí de esta forma tan eficiente. Ha salido todo muy bien, o sea, muchas gracias tanto a Gunnar como a Miguel. Agradeceros a todos que hayáis venido y hayáis participado y a los que han enviado sus trabajos para el concurso de divulgación. Muchas gracias por participar y por el esfuerzo realizado. Espero que podamos seguir haciendo concursos de este tipo en el futuro, ¿vale? Creo que dan una rentabilidad muy buena a todos y es muy eficiente de cara a difundir lo que hacemos, ¿vale? Y nada más, espero que nos veamos en una próxima edición el año que viene. No sabemos todavía dónde, pero seguro que la tendremos antes de un año. Entonces espero veros a todos muy pronto. Gracias a todos y buen viaje a casa.